One more application problem here that doesn't fall into any standard category. It's just using the kinds of tools that we've been developing throughout the course. We're told that the aerobic rating of a person X years old is modeled by this function. So you plug in the person's age as long as it's 10 or greater, and then out comes their aerobic rating. Not sure what the units are here, probably has something to do with liters of oxygen they can consume per kilogram of body weight or something, but we're not going to worry about the units. We just give some measure of how aerobically fit they are. And we are asked, according to this model, at what age is a person's aerobic rating largest? So in other words, we're being asked to find the absolute maximum of this function. Technically, we're being asked to find the x value at which the absolute max of a of x is reached. I don't actually care what the person's aerobic rating is when it's largest. We'd want to know at what age, right? So we want to find the x value at which the absolute max of this function occurs. So whichever way we're going to approach this, we know it's going to involve a derivative. So let's find the derivative of this function. This is a quotient, so we're going to use the quotient rule. So I've got the bottom function. That's, let me also point out that I can bring that factor of 110 out in front. That's just going to make the computation a little bit cleaner, right? Because this is just a constant multiple, and you're always free to bring that out. So I can pull that out and then just worry about taking the derivative of this part. And before I do that, let me point out that ln of x minus 2, when you say it out loud, it's unclear whether we're talking about ln of x and then subtract 2 versus ln of the quantity x minus 2. But the way it's written, we need to make sure that we're interpreting it this way. If you have ln and then something following it, only the first thing that's written is part of the input of the ln, unless it were enclosed in parentheses like that. And because it's not, we know that we're referring to this, not this. All right, so what's the derivative of this? It's the bottom, that's x, times the derivative of the top. The derivative of ln of x we know is 1 over x, and then minus the derivative of 2 is just 0. So that's the bottom times the derivative of the top minus the top times the derivative of the bottom. The derivative of x is 1. And that's all over the square of the denominator. All right, let's clean this up. I'll leave that 110 on the outside for now. X times 1 over x is just 1. And then minus ln of x. And then minus negative 2 is plus 2. And that's over x squared. And so I've got 110 times 1 plus 2, well, that's 3. 3 minus ln of x over x squared. And I'd like to know when this is equal to 0, because we know that candidates for when we reach a maximum are going to occur at critical numbers. Well, when is this going to equal 0? The 110 is not going to matter, right? Because that's just a constant multiple factor, and 110 is never going to be 0. So this whole thing will be equal to 0 when this fraction is equal to 0. And remember that a fraction equals 0 strictly when its numerator is equal to 0. So this will all equal 0 when the numerator, 3 minus ln of x, is equal to 0. So I need to solve this equation now for x. So if I were to add ln x to both sides and then flip-flop the sides, or if I were to subtract 3 over and then divide by the negative 1, either way we would end up getting ln of x equals 3. And then remember, to solve an equation where your unknown is inside of a natural log, we exponentiate both sides base e. Because e to the ln of x is just x, and then on the right side, e to the third power, that's x cubed. So this is our only critical number. So assuming this question has an answer, this is going to be it. Let's confirm using a sign chart that this does in fact give an absolute maximum. So here's my critical number, x cubed. Here, instead of putting an arrow, we're just going to start at 10 because this model is only valid when x is greater than or equal to 10. And then, there's probably some outer limit, maybe 130, the oldest a person has ever lived. But it's not going to matter. The derivative isn't going to change sign after this point because we only have that one critical number anyway. And so what I'll be recording here and here is, as usual, the sign of the derivative. So pick a number between 10 and e cubed. So for reference, what is e cubed? If you plug it into your calculator, you'll see that it's a little bit more than 20. So you could pick a number like 11 or 12 or 17, plug it into the derivative, and you'll find the result is positive. So that means that the function a of x is increasing on this interval, meaning the person's aerobic rating is increasing. And then you pick a number greater than e cubed, say 30 or 100, plug it into this, get a decimal, and you'll see that the output is negative. And so the function is decreasing. The person's aerobic rating decreases past this point. So if at the beginning of our model, we're always increasing until we reach e cubed and then we're decreasing forevermore, we have in fact attained an absolute maximum there. And so for practical terms, we don't talk about a person being e cubed years old. We would get a decimal for that. And again, if you do e cubed on your calculator, it comes out a little more than 20. So according to this model, an average person's aerobic rating peaks at this age. And then B asks, at what age is a person's aerobic rating decreasing most rapidly? So notice that it's not asking when is their aerobic rating a minimum. According to this function, your aerobic rating just continues to decrease forevermore until you die. But we want to know at what point is it decreasing most rapidly. So a little sketch here might be helpful to see what we're talking about. This model starts at age 10, and whatever a of 10 is, I don't care what the decimal is, but if you plug 10 into this, you're going to get some positive number. We're going to start there. I'm not putting tick marks on this axis at all because I don't actually care what a of x is. I just care whether it's increasing or decreasing. What we found is it starts wherever it starts, and then it increases until we get to age e cubed years old. And then it begins to decrease. But it's not just going to keep decreasing like this. We'll find that out actually when we do the second derivative. But if there's a point at which it's decreasing most rapidly, then that means that the concavity is going to change, right? Decreasing faster and faster and faster and faster and faster. And then past this point, it continues to decrease, but notice that it's not decreasing as rapidly anymore. So we are looking for, assuming it exists, this x value. At what age does the aerobic rating take on this sort of a shape, where it's decreasing faster and faster until then the rate of decrease starts to slow down. And I think we know from experience by now that this point that's an inflection point, right? That's where the concavity changes from being concave down to concave up. So to answer this question, we're trying to find the x coordinate of that inflection point, assuming one exists. If it didn't, then our answer would be, well, there isn't an age at which it's decreasing most rapidly. It just continues to decrease faster and faster. But the way the question is phrased, it suggests there is some point right there that looks like that. So we're going to find it. And we know that it would occur at an x value that is a solution to when the second derivative equals 0. So we need to find the second derivative of a of x, set it equal to 0, and solve. So I'm taking the derivative of the derivative. This 110, again, I can leave on the outside. And then I'm taking the derivative of this. So that's the bottom function, that's x squared, times the derivative of the top. The derivative of 3 is 0. I've got that negative, and then the derivative of ln x is 1 over x, minus the top, times the derivative of the bottom. The derivative of x squared is 2x. all over the square of the denominator. The denominator is already x squared, and when you square that, you get x to the fourth. All right, let's expand out on top. X squared times negative 1 over x is going to be negative x. And then minus 3 times 2x is minus 6x. And then negative times negative is positive ln x times 2x. I'm going to write the 2x in front. And then over the bottom. Combine these two terms. That's negative 7x plus 2x ln x over x to the fourth. Notice that this does not combine into negative 5x ln x, because this 2x is multiplying the ln x, but this one isn't. So these are not like terms, so they don't get to be combined. What I will do, though, is, oh, I missed that factor of 110 that's in front, even though it's not going to matter. I want to factor an x out of the numerator. So I'm going to have x times negative 7 plus 2 ln x all over x to the fourth. And then this x over that x to the fourth can reduce. And so I'll have negative 7 plus 2 ln x over x cubed. This now is the fully simplified form of our second derivative. So now let's find out when that equals 0. I want to know what value of x is going to make this equal to 0. Well, again, the factor of 110 isn't going to affect whether it's 0 or not. And then it's 110 times a fraction. And again, a fraction equals 0 when its numerator is equal to 0. So the second derivative will equal 0 when negative 7 plus 2 ln x equals 0. And then we solve this. Add 7 to both sides, and then divide by 2. I'll get ln x equals 7 over 2. And then to solve for x, we're just exponentiating both sides base e. E to the ln x is x, and I get e to the 7 over 2. So that is the coordinate of that key point, which is the answer to this question. So the answer is that a person's aerobic rating is decreasing most rapidly at age e to the 7/2, which in practical terms, plug that into your calculator and you'll see that it's about 33.12 years old.